Hi Irritants, and welcome to the fifth and final video in this series on algebra skills for maths methods. It's been a pleasure teaching you this year, and I want to wish you all the best for your future studies. If you come back to this channel in the future, you might see some Year 12 methods videos, because that's what I'm teaching at the new school next year. So with that underway, let's take a quick look at simplifying surds. So I want to begin by telling you a little bit about the different kinds of numbers that we use in mathematics. The simplest one is the natural numbers, and that begins with 0, 1, and 2. These are sort of like your positive, or I should say non-negative counting numbers. So we often use them to answer questions such as how many chairs are in the room, how many people are in the room, how many fingers are on your hand. And usually we answer these sorts of questions with whole numbers. And the natural numbers support addition and multiplication. They don't support subtraction, because if I do 1 minus 5, I can't find a number in the natural numbers such that if I add 5 to some number, I get 1. If I add, I can only go up. I can't go down. To go down and go past 0 to the negative numbers, I need to extend the natural numbers to the integers, and that allows me to introduce the subtraction operation. So the integers are any positive, negative, or 0 whole number, and you'll notice that I haven't used the word whole number on this slide, and that's because it's ambiguous. If you go on in mathematics, you will use the terms natural numbers and integers. You won't use the word whole numbers. So we've got addition, we've got multiplication, we've got subtraction. So now I can talk about negative temperatures, overdrawn accounts, being underground in a building, but I can't really talk about parts of a whole yet. In order to talk about parts of a whole, or fractions, I need to extend from the integers to what are called the rational numbers. And at this point, now I can use the division operation. So we define the rational numbers to be a fraction where the numerator and denominator are integers, and of course the denominator can't be 0 because division by 0 is undefined. And up until this point, I'd say end of year 8, the rational numbers are sufficient for doing all of mathematics. Unfortunately, it's not enough. The Greeks discovered this. If I draw a right-angled triangle with side lengths of 1 and 1, using Pythagoras' theorem, we get this mysterious length root 2. And it turns out I can't express this number root 2 as a rational number. If I try, I fail. Feel free to look it up or ask me about it in class. So again, as we did before, to introduce this notion of root 2, I have to extend the rational numbers again. And the question of what we define the real numbers to be and what operation we introduce to do this is such a deep question that it's usually left until university. So I'll just give you a little bit of a hint. It's going to involve something called a limit, but I'm going to leave what we put inside this box undefined, as in I'm going to invite you to do some research or go on and take mathematics after school. It truly is a beautiful story and one that I highly commend to you. When you take calculus and methods, you are assuming that you have access to the real numbers, so there are no gaps in the number line. So what does all of this have to do with surds? Well, surds belong in the real numbers. Specifically, they belong in this set Q prime, which is the set of irrational numbers. So if you're seeing surds for the first time, you need to be aware that this is a new kind of number that you have not worked with before. And they're unlike any of the other numbers you worked with. We can't write them as a fraction of two integers. So to start the show today, surds, just remember that it's a new kind of number. And while I'm not going to be rigorously defining it, I'm just going to show you a few properties of this kind of number, and then we can do some calculations of it. Okay, so you might have seen this notation before, root x. And you might ask, what exactly do we mean by this? So for example, if I gave you the number 8 to the power of half, or root 8, what is this number doing? What is the property of this number? Well, what I want is for root 8 to be a number such that if I square it, I get 8. And if I take 8 to the power of half, square that, I get 8. I haven't told you how to calculate the number. I've simply said what I want the property of that number to be. Now, 8 doesn't work. 8 is not a perfect square. However, the number 25, that is a perfect square. So if I conceive of a square root of 25, I can actually write down the exact number 5. However, if I try to do this with root 8, I'm stuck. If you do it on a calculator, you get this long string of decimals which never repeats. There's no pattern to it. So what do we do? Well, one thing we could do is write out the decimal digits, but we would be writing forever. Another thing we could do is approximate, so round off the decimals, and sometimes that's a useful thing to do. The last thing we can do is simply write root 8. So whenever I write the word root 8, I'm not worried about what the exact number itself is, what the digits are. I'm just going to treat it algebraically as an object, where I know what the property of this number is going to be. Okay? So I've defined a number by its property, but I haven't told you how to calculate it. You might feel uncomfortable with that, but it's okay. If you go on in maths, you can figure out how to calculate the square root. It's not the easiest thing to do, but it's not too bad. Now, we can go further. We can define the cubed root and the fourth root. We can go on forever. You might wonder why there's no 2 here. So it's assumed that if there's no number written next to the radical symbol, the square root is implied. Okay? So we've defined roots or fractional indices by their property. And it turns out some of these roots generate surds, like root 2, root 3, and root 5, because I can't simplify them to a fraction of 2 integers. I can't simplify them to a rational number. However, root 4, root 9, and root 16, they do simplify. They simplify to the numbers 2, 3, and 4, respectively. So you just need to keep in mind that just because we have a square root symbol, it doesn't mean that we have a surd. It's only a surd if the number underneath the square root symbol isn't a perfect square. Be right back. Okay, so I know it was a bit technical. You'll have a chance to go over this again next year in methods. So now I'll just quickly show you the most commonly used square roots. There's nothing new here, provided that you know your times tables. And I hope you do. If you don't know this slide off by heart and you don't know your times tables off by heart, I suggest you learn them before you start in methods next year. It will make life a lot easier for you. Okay, and this is the last slide. So I'm just going to do 4 examples, and then we will wrap it up here for the Year 10 course. So here I'm going to give you a rule. The rule is, if I have 2 numbers a and b, and I take the square root of a times b, that's the same as taking the square root of a times the square root of b. So some people will write it like this. I've written it more compactly here. Now you might wonder, why does this work? Well, one of the index laws states that if I take a product a times b and raise the whole thing to the power of n, then I get a to the n, b to the n. So if I take ab to the power of a half, I get a to the power of a half, b to the power of half. So while this might look like a new rule that came from nowhere, it's actually an application of the index laws you already know, with the special case where the index is half, and it might be the first time you're seeing this. Okay, so why do we want to use this property? The reason is, if I can write the number underneath the square root as to be as small as possible, I want to be able to do that. In particular, this number a, if I can choose a to be a perfect square, then I can actually write that number out the front and multiply a smaller square root. So let me show you what this looks like. When I look at the number 50, I'm noticing that 25 is a perfect square, which is a factor of 50. So I can split 50 into 25 times 2. And now I can simplify root 25 because I know those perfect squares in the previous slide. Root 25 is just 5. So now I claim that root 50 is the same as 5 times the square root of 2. And somehow I hope you agree with me that this number, 5 root 2, is simpler than root 50. I've got the same quantity, but I've used smaller numbers to describe it. And that's all we're doing here, and that's all you need to know from today's lesson. Okay, let's look at the next one, root 75. Well, the number 25 divides 75 with no remainder. So I can write this as root 25 times root 3, because 25 goes into 75 3 times. And now I can simplify. So now I can write 5 root 3. Okay, what about root 80? Certainly the number 4 works. 80 is the same as 4 times 20. There's actually a bigger factor we can use here. We can use 16, because 16 times 5 gives us 80. Now, root 16 is 4. So we get 4 root 5 as the simplified form of root 80. Now, one question you might have is, what if I didn't notice that 16 was a factor of 80? What if I only saw the 4? Well, that would have been okay. Let me show you. So suppose I only saw root 4 times root 20. Then I can write this as 2 root 20. And now I can simplify root 20. I can see that root 20 is the same as root 4 times root 5. Now I can't drop the 2 because I've got 2 root 20s. So it's 2 times root 4 times root 5. Root 4 is 2, and 2 times 2 is 4. So I actually get 4 root 5 as well. So that's an alternative. And that's perfectly fine. Okay, last one. Root 4900. This is a massive number. It looks like a mess. But the 49 looks very tantalizing, doesn't it? What happens if I divide 4900 by 49? Well, I get 100. So what we have is root 49 times root 100. And actually, both of those evaluate to rational numbers. It's 7 times 10, which is 70. Which means this is actually not a surd. Although it has been written with a square root symbol, this number 70 is a rational number. So it wouldn't be correct to call it a surd. There are other properties of surds that you will learn about next year. But I just wanted to show you a little bit this year because I really do think that a year 10 student should learn something about surds. And I guess the more you see earlier, the easier it is later. So I hope you've enjoyed this brief tour of surds, and I hope you've enjoyed the year as well. If you've made it this far in the video, I want to wish you all the best for your future studies. It has been a pleasure teaching you. Take care.